All right. Okay, so we're ready to start looking at sample problem 17-2, and this is going to be a gear problem. I like these. They're application of the things that are, things that you see in our program, but then also we see gears all over the place out in industry. So I'm going to check here. In my physics class, they used, UG for potential. Okay, all right. Um, so here is the illustration of the driven gear is going to be the larger one here. That's going to be gear A. The driver is going to be gear B. And you're going to notice that there's an M for a motor that is going, or it's the moment, but it's caused by a motor that is going to actually, drive that gear B to go around in a counterclockwise direction, which then engages with A, and then A is going to go in the opposite direction. You're also going to see that we're given the physical sizes here of the radiuses out to their pitch diameters, okay? Both given in millimeters, so if we find that we have to use those radiuses, we're going to have to make sure that we put those in the appropriate units like meters for our problems. They're letting us know that the mass of gear A is 10 kilograms and its radius of gyration is 200 millimeters, okay? And then B, 3 kilograms, and its radius of gyration is going to be 80 millimeters. Now, they want us to do this in two parts. First, we want to determine the number of revolutions that the gear needs to get up to an angular velocity of 600 RPMs. So it's starting from rest. We're gonna give it this moment, okay? This rotation torque, really, in the case of a rotating gear, but they're calling it moment here, which is fine. And we want to know how many rotations is it going to take us to get to 600 RPMs. Okay, that's going to be the first part of the problem. And then the second part of the problem wants us to determine what is the tangential force that's exerted by gear B on A. Okay, so we are going to be looking at part A first. Now, in this case, part A, we're trying to determine the number of revolutions of a gear. We are going to be using the work energy theorem because, and I'm going to go underneath here, underneath my camera, because in the work energy theorem, in the work here we've got, angles, and this is going to be in radians, but then we can convert it to revolutions. So we're going to be using that moment, and we're going to be finding that. So we're going to use the work energy theorem up here, and then we'll be able to solve for the revolutions. So what I got started here was just the illustration, so I wouldn't be taking up too much time at the beginning of the problem here. So this represents gear A, gear B. I kind of have their rotations, the moments that's going to be induced, their radiuses, and then also their common velocity 2 that we see here, okay? And we'll talk that through in a little bit. I do want to put my givens, which are mass A is equal to 10 kilograms. Radius of gyration around A is 200 millimeters, which is going to be equal to 2.2 meters. I'm going to convert that right away. Just moving the decimal place, you don't have to show that. I know in metric, it's way easy. 3 kilograms for B. Hey, B is 80 millimeters, which is equal to 0.08 meters, 3 decimal places to the left. And then the moment around B that is like inducing the rotations is going to be 6 Newton meters. Okay. We need to find, and this is 2 parts. In part A, we need to find theta in revolutions when W2B is equal to 600 RPMs. And that means it's going to be its final. So we're starting out at rest here. We're going to be applying that moment or that torque of 6 Newton meters. And we want to know how many revolutions to get to 600 RPMs. And that'll be the W2, if you would, of our gear B. And then the second part of this is going to be the tangential force B on A. okay, the tangential force. So we'll look at that in part B. We can say that our V1 is equal to 0. Okay, and that's going to be this, you know, as we start here, we're not going to be moving, it's going to be at rest. And then V2 is going to be the final velocity. Okay. All right, so our approach, as we already said, we're going to use the work energy theorem. So we know that that's going to be T1 plus U1 to 2 times T2. And because of our velocity 1 being 0, this is going to go to 0. And our equation is essentially just going to be the work is equal to the final kinetic energy. So we've got a rotating body. We don't have any translational motion. Okay, so we only have these two rotating bodies that are rotating about their own fixed center. So our T2 is going to be equal to 1/2 moment of inertia of A times angular velocity of A squared plus 1/2 times moment of inertia of B times the angular velocity of B. And we're going to call that 2 and 2 squared because it's going to be the final velocities, right? All right. And then our work is going to be our moment times theta V. The 1 is starting from rest. This would be the 2, so this would be theta 2. Okay. So that's how we're going to get there. So as we look at, just kind of peeking ahead here, our angular velocities. Okay, we know that our ending angular velocity needs to be 600 RPMs. So the first thing I'm going to do, and we'll get back to these equations here, but we're going to kind of get our terms. So we need these W's, right? So we know that WB2 is 600 revolutions per minute, and we need to convert that to radians per second. So 1 revolution is 2 pi radians, and 1 minute is 60 seconds. Okay. So our W2B, when it's at that 600 RPMs, it's going to be 62.83 radians per second. Okay. And this is the value we're going to use up here. Okay. So that's that value directly. But now I've got to figure out what is my angular velocity of A. Now we have 2 gears. We know now the angular velocity in radians per second of B. I've got to figure out what this is. We're going to use these radiuses, the ratio. So we're going to figure out the velocity ratio between A and B. We're going to use that velocity ratio to find out what WA is. Okay. So our velocity ratio A to B is going to be equal to, now if you have to look back at the bottom of our equation sheet, velocity ratio, we have radiuses. So we're going to take the radius of the driven, which is A, divided by the radius of the driver, which is B. So we're going to take RA divided by RB. And we know that RA 250 millimeters divided by 100 millimeters. Now, because this is a ratio, in this case, you have a choice. You can leave it in millimeters or you can put it into meters. Totally up to you. Just to be consistent, so we don't forget, I'm going to put mine in the meters. So we'll get the same answer in the end, but I'm going to say 0.25 meters for radius of A and 0.1 meters for the radius of B. Meters cancel out. If you do 250 and 100 millimeters, they'll cancel out and you'll get the same value here. And our velocity ratio A to B is going to be 2.5. No units, okay? No units. So now, since we also know that the velocity ratio is equal to W1, which is the driver, that's going to be WB, divided by WA, which is going to be driven, we can, velocity ratio, A to B, it's going to be WB divided by WA. Okay. And if I rearrange that to solve for WA, okay, WA, I'm going to say that WA is equal to WB divided by the velocity ratio of A to B. Okay. And when I say WB, I mean WB2. It's just that it's in the second state. We're looking at that second side of things. And now I know that my W2B is 62.83 radians per second divided by my velocity ratio of 2.5. Okay, that means that my WA is equal to 25.132 radians per second, because it's radians per second divided by nothing, right? As far as units, because that's just a ratio. Make sure you get the same value as me. So now, if we look up here in our equation, we've got WB2, we've got WA2, should put the 2 behind it, okay? We know, do we know the, oh no, we have to calculate our moments of inertia. That's going to be the next thing, okay? We do know radius of gyration and mass, so that'll be helpful. So let's find the moments of inertia. So we'll do A first. We know that's going to be the mass of A times K of A squared, which is going to be equal to 10 kilograms times, now remember, it gave it to us as 200 millimeters, so we're going to multiply it by 0.2 meters squared. So my moment of inertia about A should be 0.4. So I don't use mechanical pencils. I'm always breaking my little tip here. And I'm going to do the very same thing for B. Moment of inertia about B is going to be the mass of B times KB squared, which is equal to 3 kilograms times 0.08 meters. 0.08 meters squared. So you should get 0.0192 is the moment of inertia of B. Now, as we look up here, we've got those two done. So we've got the moments of inertia done. So we have all of our kinetic energy done. Okay, kinetic energy of 2 done. All right. Then we are going to do our work. Okay, so I'm going to turn this over. And I know that my work 1 to 2 is going to be equal to moment times theta B. Okay, moment times theta B. Now, theta B is what we are going to try to find. Okay, our moment is given to us. That's the moment that the driver is creating to get sped up, and we know that to be 6 Newton meters. So we know what that is. So now if we take our equation, work is equal to T2. We go over here, this is going to be our mass theta B. I'm sorry, moment theta B, our 1/2. I'm just rewriting this so it's all on the same page. If you don't want to write this over again, I totally understand. WA2 squared plus I the WB2 squared. All right, so now I'm going to put my values in on either side, and my theta B is going to be left over. So I know that this is going to be 6 theta B is going to be equal to 1/2. So now I'm going to go back to my first page, 0.4 times WA2 25.132. And I have to square that. Plus 1/2 times 0.0192 times WB 62.83 squared. Now to solve for our theta B, we're going to take all of that and divide by 6. I'm going to give you a chance to calculate that. I'll just write the values here. The chance to make sure you can get that number.
That's what I got.
Awesome. Okay. All right. So we have this in radians, but remember, our problem was asking us how many revolutions, right? So we've got theta. All we need to do now is convert it. So I know that there's 2 pi radians in 1 revolution. Okay, so radians cancel out here. And part A, my theta B is going to be equal to 4.356 revolutions. Okay, and that's to get to 600 RPMs. That's pretty darn quick. I'm like, that little gear, well, at least in the picture, it looks little. That little gear only has to go around 4 times to get up to speed to 600 RPMs. Doesn't that seem, maybe 600 RPMs, maybe it's not that fast. I guess it's 600 in 1 minute. That's 1 or 10 revolutions every minute. Maybe it's not that fast, but I don't know. It just seems like a small little number. All right, so that's part A. Any questions, or do you need to see anything that we did here? Sure. So we're ready to look at part B. Okay, part B. Part B, we want to find out what is that tangential force on A due to B. Okay, due to B. So we're going to look just at gear A this time. All right, so we're just going to look at gear A because this is the one that we're analyzing. Okay, so this is gear A. We know that it's going WA that way. We know that it has a radius and that this is also the place where that force is going to, come in. So B is down here and B is rotating and it's engaged with the teeth on A. And this is the force that's actually going to push on A to get it to rotate on each one of those gear teeth. So we know that this radius here, 250 millimeters, right? Okay. So we're going to use the work energy theorem again. Okay. So we're going to say T1 plus U1 to 2 is equal to T2. We know that we're starting from rest, so T1 is going to be equal to 0. And this time, I guess I'm going to call this T2A just because I don't want to mix it up with what was on top. Now, the work part is going to be equal to force times distance. Okay. Yes, this is rotating, but we're trying to find that tangential force. And if you remember, this was an extra little equation that we expanded out here on our equation sheet where the tangential force is going to be equal to the radians times the radius. Now, the radians for which they're going to go through, okay, we're gonna calculate that. So we are going to say that's equal to force tangential times theta times RA. Okay, and we know RA is down here. But our theta is equal to distance over radius. And our distance over radius, where the heck did I? Oh, yeah, okay. Now, it's a little subset here. We know that our velocity ratio A to B is equal to theta B, the driver, over the driven. And this is one of these guys right here. It's this one. So driver over driven. Okay, so the driver was B over the driven. We know that our velocity ratio is 2.5. We know the theta of B. We know how many radians it goes through right there. So we're going to use that 27.37 for B. We have to find out what are the radians over here. What's the distance that this goes around on the circumference? Okay, so we know our velocity ratio, we know our B. So we can say that theta A is going to be equal to theta B divided by the velocity ratio A to B. Okay. And that's just rearranging via algebra. So now we're going to say theta A is going to be equal to, we're going to take that 27.37 radians divided by 2.5, which was our velocity ratio from earlier. And our theta A then is 10.948 radians. Okay, and that's what we're going to use up there. Okay. So this is going to be equal to FT times 10.948 times the radius. Here equals FT times 10.948 times 0.25. And I'm just going to put the meters there because we're going from 250 millimeters to 0.25 meters. It has to be in meters. So that's what our work is going to be. Our multiply those values out. U1 to 2. It's going to be 2.737, multiplying those two together, times FT. Okay. So that's going to be the work in our equation above. Now we've got to do the T2. Okay. So our T2 is going to be equal to 1/2 IWA squared. Okay. Because we were just worrying about gear A right here. That's going to be equal to 1/2 times 0.4 moment of inertia. And we know WA to be 25.132 squared. That's radians per second. That was from the first page. Okay. So our T2, we'll call that A, it's equal to 126.323. And that's Newton meters, just so you know. It's not a final answer, so you don't necessarily have to put that in there. So then now going back up to our work is equal to our final kinetic energy. U12 is equal to T2A. We can now put this value for the work, 2.737 FT, that's our unknown, is equal to 126.323. Dividing both sides, 2.737. Our FT, 46.154, and that's going to be newtons. That is the force then that is transmitted when gear A and gear B are in mesh. Okay. Now, recalling when you guys have had gear calculations in machine design elements, that tangential force is the one that is the one that we have to worry the most about, because it's going to be the one that's going to shear off the teeth, right? It's also the one that's going to create the pitting stress that's there. So knowing that force is important. All right. Any questions on this problem? So that's part B. If not, I'm going to stop the recording